Okay, folks, so Elizabeth asked me to make a video of this, and it seemed like a lot of sense, so I'm going to go ahead and do this. So let's talk a little bit about hybrid orbital theory, okay? So remember, the reason why this doesn't work is um, if we look at our carbon, my carbon is 1s, 2s, right? And um, 2p. And so if, oops, excuse me, got way too many bonds, electrons here for my carbon, right? We only have 4 valence electrons. So there's my carbon. Let's say we're going to bond methane, right? So I would want to promote an electron. So we'll get rid of that electron in the 2s and we'd put it up here. And then I'd have my hydrogens, right? 1s, 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 oops, hydrogen 1s, and a hydrogen 1s, right? And then we'd have the overlapping occurring, right? And so then we'd have 4 bonds, but we'd have one bond that is a 1s to a 2s, and 3 bonds that are 1s to 2p's. So we'd expect that one of these bonds would be shorter or different than the others in my methane. And that's just not the way reality is. In methane, all 4 of these bonds are the same type. So that would suggest that this bonding or the orbital overlap, atomic orbital overlap, does not work. And so we need to then start over with a different kind of a theory, and that theory is hybrid orbitals, right? So what we're going to look at is we're assuming that we're going to take our 4 valence orbitals. We have an s and then like a px, a py, and a pz. And we're going to take those, and depending on the demand, we're going to change those into another orbital. Now, here's the real reality, right? We know that these orbitals don't really exist, that they're only mathematic probabilities. So what we're really saying is when we compare the likelihood of finding an electron in an atom, it's different than where we might find them in a molecule. And so the shape of those orbitals are going to change. Now, we start out with these 4, and we really have 3 different possibilities. I could end up where I have 2 hybrid orbitals. We call those 2 sp orbitals. So if I end up with 2, I'm only using the s and one of the p's. That means I would have 2 other p orbitals that are still unhybridized. That's one type of hybridization. Another type of hybridization is where I'm going to use an s and 2 of my p atomic orbitals, and then those are going to be replaced by what we call sp2 orbitals, right? sp2, sp2, sp2 orbitals. So I have 3 sp2 orbitals, but notice I still have 1 p that hasn't been hybridized, or we still have 1 area on the atom that still has the likelihood of finding an electron in something that looks like a peanut, right? And the third type, so this is what we call sp hybridization. This is sp2 hybridization. And then could have sp3 hybridization. And in that case, I'm going to use the s. I'm going to get rid of the s and all 3 of the p's, and those are going to be replaced by 4 sp3 orbitals. Okay, oops, sorry about that. Don't need to put any electrons in there. And so I have 4 sp3 orbitals, and there will be no unhybridized orbitals when we have an sp3 hybridization. Now the question is, how do I choose which of these hybridizations to use? And we're going to base that upon my electron domains, okay? So if I have 2 electron domains, I'm going to go with the sp hybridization. If I have 3 electron domains, I'm going to go with sp2 hybridizations. And if I have 4, then I'm going to go with my sp3 hybridization. So what's the process when I look at a problem that I'm going to follow? First thing I'm going to do is draw my Lewis structure. Once I have my Lewis structure, I'm going to identify my electron domains. And then once I have my electron domains, I'm going to choose my hybrids based upon right here. All right? Okay, so that's the basic idea of what we're doing. Now, let's go ahead and work some of these. Let's do my methane, right? So here's my methane. So I draw my Lewis structure, right? And I have what? 1, 2, 3, 4 electron domains. So I have 4 electron domains. So when I look at that, that suggests that I'm going to use sp3 hybridization. And when I use sp3 hybridization, how many of those do I have? 1, 2, 3, 4. So all 4 of my atomic orbitals would be replaced with 4sp3. So let's start from the beginning. Here's my carbon. I have a 1s, I have a 2s, and I have a 2p, right? Good. Now, let's go ahead and promote this electron. And so I'm going to promote it, meaning I'm going to put some energy into that. And so that means this electron goes here. So now I have 1 electron in each orbital. And so now those orbitals can overlap with another orbital, right? Then I'm going to go through the hybridization process. And these 4 valence orbitals will be replaced with what? 4 sp3s. 1, 2, 3, 4. Oops, we have to have our 1s. So here's my 1s. And now I have 1, 2, 3, 4 sp3s. Each of those has an electron in it. And now we can lay down my hydrogens. There's my 1s for a hydrogen. Here's another hydrogen, 1s. And here's a hydrogen, 1s. And here's a hydrogen, 1s, right? And then what would happen? This 1s and a hydrogen would overlap in sp3. 1s and a hydrogen overlap in sp3. 1s and hydrogen overlap in sp3. 1s and hydrogen overlap in sp3. Good. So that's how this would work. Now, the one other thing we can add to this is this idea of sigma bonds versus pi bonds. So sigma bonds and pi bonds. Sigma bonds, these things have their bonding density in the internuclear axis. Okay, that means if I draw a line between my 2 nuclei, my bonding density lies on it. So here's one nucleus, here's the other nucleus, and so then I'd have a bond like, I mean, something like that. And oops, no, it wouldn't be like that, would it? It would be something like I have this and I have that, and there's a bonding density here, and here is an axis, and so that bonding density is in the nuclear axis, so we call that a sigma bond. Now, what kind of things usually have sigma bonds going on with them? All my hybrids are usually sigma bonds, all right? So these guys are usually my hybrids, orbitals, in the hybridized atom, okay? My pi bonds, these are above and below. So let's say I have a nucleus here and a nucleus here, and they're bonded here, and so this would be a sigma bond, but then they also bond above and below, and so that would be the pi bond. And I know it looks kind of weird, but that's what's really happening. I'm likely to find that second bond, my pi bond, both above and below the internuclear axis, right? It looks like Santa Claus with some kind of tattoo on his forehead, doesn't it? Okay, good. Now, what's really important for us to know is single bonds are made up of sigmas. If I have a double bond, I've got 1 sigma and 1 pi. And if I have a triple bond, Then I have 1 sigma, and I have 2 pi's. Sure. Yeah, so sorry about that. We're also having lab questions go here. So give me a second, and we'll pause. I might make sure they don't blow themselves up. Okay, I'm back. So yes, so we have a single bond, it's going to be a sigma. If I have a double bond, it's going to be a sigma and a pi. And if it's triple bond, it's going to be a sigma and 2 pi's. Now, the thing about it is, the things that are going to be forming the pi's are usually going to be my unhybridized p's, all right? Sometimes I can use d's, but most of the time I'm going to be using unhybridized p's. So that would mean that if I have all single bonds, usually I'm using sp3. If I have a double bond somewhere, I can't use sp3. If I only have 1 double bond, it's usually sp2, so that I have that extra pi available for the pi bond. I mean, extra p for the pi bond. And if it's a triple bond, then usually what I have going on is my sp, so I have 2 unhybridized p's, and these guys are the ones that are involved in the pi bonding. All right? So now, let's go and take a look at this question right up here, right? I've got C2H4. So here we go, C2H4. Let's work that out. C2H4 is this kind of Lewis structure, right? So let's take a look at the hybridization or the bonding around this carbon, right? I've got 1, 2, 3 bonding domains, or excuse me, electron domains. So if it's 3 electron domains, I'm going to go with what? sp2 hybridization, and that would mean I would have 3 sp2s, and I would end up with one unhybridized p. So here we go. Let's see how this works. Oh, same thing on this side. I have 3 electron domains as well, right? So here we go. I have my carbon, 1s, and I'm going to then hybridize it. So it's going to be 1, 2, 3 sp2s, and then the 2p is unhybridized. So 1s2, and then 1, 1, 1, 1, right? I've already promoted my electron. We'll call this carbon 1. Carbon 2, we're going to do the same thing with it, right? 1, 2, 3, because it has 3 electron domains. So this is sp2. Good. And then I have an unhybridized p, right? And then I have what? 2 hydrogens on both sides. So here is a hydrogen 1s, and here's a hydrogen 1s. And up here I have a hydrogen 1s and a hydrogen 1s, right? And so now I start looking at my bonding. This hydrogen bonds with the carbon number 2. This hydrogen bonds with carbon number 2. This hydrogen bonds with carbon number 1. This hydrogen bonds with carbon number 1, right? And now my 2 carbons start to bond. Here is the first bond, and it's between an sp2 and an sp2. So that means that's going to be the sigma bond. And then here I have my 2 p's overlapping. That makes my pi bond. Each of these hydrogen bonds are going to be sigma bonds, right? So then how would I explain this? I'd say what? 1s in each hydrogen overlaps what? A sp2 in C1 forming sigma bonds. And then I have 1s in each hydrogen overlap. I should say overlap, right? The 1s in each overlaps. That'd be correct. Overlaps sp2 orbitals in C2 forming sigma bonds, right? And then now what happens? What is happening between my C1 and C2, right? So I have an sp2 in C1 overlaps an sp2 in C2, right? Forming what kind of bond? Forming a sigma bond, right? And then I have my 2p in carbon 1 right here, right? I have my 2p in my first carbon overlaps a 2p in my second carbon, forming what kind of a bond? This is the second bond, right? And it's between my two p's, so this is forming pi bond, right? Good. And so when I look at this in total, so I have this, right? H, and H. I would have a sigma, 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 pi. So I'd have 1, 2, 3, 4, 5 sigmas, and I have one pi bond. There we go, folks. That is essentially your hybridization along with throwing in the concepts of sigma and pi bonds. All right, I hope this helps.